Hi, so in this video lecture, we will be talking about digital to analog converters. So again, this is for EEE153, week 6. So our coverage are just DAC examples and the DACs of the PIC32 or lack thereof. So relative to ADCs, DACs are very simple. So for example, here we have the flash DAC, which is similar to the flash ADC, just uses a resistor ladder network for a fast way to generate a fraction of the voltage of the reference. So in this case, you would want to use a switch decoder so that your digital DAC code can be converted to the proper switch. So if you have a DAC code of 000, this switch will be closed. If you have a DAC code of 101, you will get to closed switch number 5. Now, the problem with this is that these switches, we don't expect them to be mechanical switches, rather solid state switches in MOSFETs. So if we have a lot of MOSFETs connected to a single node, we'd expect that there is a large capacitance in this node, therefore it might get a little slow. So we usually employ multiple switches in this manner in such a way that you don't really need a switch decoder anymore. You can feed your bits to the switches themselves because in this case, for this node, the capacitance it will need to, since the switches are connected in series, capacitances in series will not increase each other, therefore it won't be that slow anymore. Now, yes, the additional switches alleviates the loading and generally speeds up the system, assuming the switches are ideal. However, still, similar to flash ADCs, our number of resistors will scale exponentially. And that is also true with the number of switches that we have. So more switches, more resistor means it's very expensive to get a larger DAC when using this architecture. So we have here the R2R ladder DAC, wherein we have two R resistors connected to a switch controlled by our bits, which either connect to the ground or the reference voltage. And between them are resistor values of value R. Then lastly here, we have a 2R resistor connected to the ground. So in order to see how it works, let's use an example. If we have a VREF of 1 volt and a DAC code of 100, that means X3 will be on or connect this 2R resistor to VREF, and the others will be connected to ground. Now since 2R is connected to ground and it will be in parallel with the other 2R resistor here in the bottom. So after we combine those, we can see that this resistor over here is connected in series with this R resistor. Now, since it's connected in series with this resistor, we can combine them, and you can see 2R is again, 2R resistor is again in parallel with 2R resistance here. So we can actually simplify this whole network up to this Vout node to just 2R. Now, if you didn't get how that happened, I'll just I'll just pause the slide here and you, I guess, think about it. Now, since we have two 2R resistors connected in series, this is an operational amplifier, or rather, our VREF here is connected to two 2R resistors. Since we don't expect current to flow here, we can easily use voltage division to get the value of Vout, which is half of our VREF. Now, for another example, let's say the DAC code is 010. So instead of X3 being connected to VREF, we say X2 is connected to VREF. Now, the resistors over here to the right will simplify to R. And since we have a resistor here, uh, this 2R resistor will be in parallel with this combination of resistors to ground. Therefore, we can get the voltage at this node by using voltage division. So the voltage connected, the resistor connected to ground is 3R in parallel to 2R, and then the total resistors will be this one. So we get the voltage here to be 3/8 or V reference. And then to get the voltage at V out, we simply divide the voltage again since we have 3/8 of voltage here, and then an R resistor and the 2R resistor connected to ground over here. So we can say that the V out at this configuration will be 1/4 of the V ref. So actually, if we want to summarize that, if our DAC code is 100, our V out is 1/2. If our DAC code is 0100, our V out is 1/4, which should be expected given how we convert from our DAC code to an output, an analog voltage reference. But if we want to continue this pattern, I think you can do it on your own, but you can find out that a DAC code of 0010 will output a V out of 1/8, and a DAC code of 001 would output an analog voltage of 1/16 of the VREF. And we can think of the switches as connecting to a new VREF source, so we can actually combine these and use superposition to calculate our other voltages. So if we have a DAC code of 1010, we just need to add the voltage output of DAC code 1000 and 0010, which is 1/2 plus 1/8, which is what we would be expecting when we have, which is the analog voltage we would be expecting when we have a DAC code of 1010. So, why do we have to use some complicated ladder network, such as, well, this is not yet that complicated, but still, we can use differently weighted resistors for the bits so that we can have a simpler design, like this inverting summer DAC. Although the problem here is the resistors we have here need to be very precise. This resistor needs to be exactly twice this resistor, and this one needs to be exactly twice this, and we need to have a resistor that is exactly 16 times R. So in comparison, you can easily make resistors that are twice another resistor by simply connecting two of them, but it gets really tedious when we get here. And then another problem is our output here is negative, and we might not want that. So for commercial DACs, our outputs will either be current or voltage. So most of our examples are in voltage. Then as a point of reference, we have DACs that have up to 16 bits of precision. Then apart from accuracy, a key metric for DACs is the settling time, or the time needed before the DAC output is stable. So upon setting the DAC to the DAC code you want to generate an analog quantity from, the settling time tells how much time you need to wait before we get that stable value. So for the PIC 32, we don't have a dedicated DAC peripheral. However, we do have a comparator voltage reference from the comparator module, but it's not really a DAC, rather a configurable voltage reference. Nonetheless, you can still use it as an analog voltage output. Another alternative is to use pulse width modulation using the output compare module. However, this will be explained further in a future video. So first we have the comparator voltage reference, which is a 16-step resistor ladder network. And then you can internally connect, the CVR is internally connected to the comparator modules, but can also be connected to an external output pin. So it has a high and low output range since it's not really a DAC, especially since you cannot compute the output of the CVR without by using the normal way, which is the DAC code times the voltage reference over the maximum or 2 to the resolution. So the block diagram is like this. So we have a resistor ladder network here with a multiplexer selecting the voltage output between them, or the voltages between them rather. So we can see here that we have a reference select. Similar to the ADC, we can connect to a external VREF pin or to the analog VDD pin. Then we have an enable buffer here in order to enable our comparator voltage reference. So same with the negative reference, we can select analog VSS or the VREF minus pin. So we have here a range select transistor, which connects an additional 8R resistor to the ladder, increasing the voltage output. So that means whenever CVRR is 1, our CVREF is this equation. So as you can see, it's not really um, similar to what we use for our DACs. And then when CVRR is 0, we use this equation. So as a quick reference, here are the possible voltage outputs that you can generate with your CVRR, given a reference of 3.3 volts. So seeing here at CVRR equals 1, our voltage steps are in steps of 0.14 volts, and when CVR is 0, our voltage steps are in 0.10 volt increments. So you can see here, it's not really a can't really say that it's a DAC, but nonetheless, it is an analog voltage reference source. So next is pulse width modulation, which is a digital technique when we have a slow, right, when we need a slow analog output voltage. So the premise is that we use increasing pulse widths to generate a higher average voltage and smaller pulse widths if we need to generate a smaller average voltage. So you'll have more information on this on the succeeding videos, but I think you have a good idea of how it works using in this figure. So in summary, relative to ADCs, DACs are quite simple, but the architecture and the choice of components still matter a lot in separating good and bad DACs. So with whichever architecture you're using, uh, can greatly affect the settling time, the noise, and the accuracy of your DAC. And then sadly, the PIC32 does not have a built-in DAC peripheral. However, it has ways to generate an output that is analog still. And this is also, and apart from that, in the succeeding topics, you will get to know how to actually use external DAC peripherals for your microcontroller. So that's it for this video lecture. Thank you for listening.